All right, guys, so we're finishing up the note sheets for today, 5.23, this addition and subtraction. And that's really what the last thing we're going to be covering here. We have a few problems left that we'll cover dealing with this here. We talked about A yesterday, and we saw that 5 times the square root of y plus 6 times the square root of y is 11 square root of y. We can add those together. Now, B, on the other hand, because the radicals, well, they do have the same index, but because what's inside of them is not the same, we can't just add them. So we need to simplify these down. Now, when we look at this here, and I believe we started looking at this yesterday, we had 2z to the 5th we need to simplify, and the cubed root of 54z squared. These are the two that we really need to simplify down because they do have factors or cubes in them. Now, when we look at 2z to the 5th, well, 2 is not something we can reduce because the cubed root of 2 is just going to be the cubed root of 2. There's nothing we can pull out. Cubed root 2. Now, z to the 5th, we can reduce that. We can take the cubed root, or at least a cube, out. Because we have how many total? 5, and we can pull out groups of 3. So if we do, I'll have to write it up here, 5 minus 3, well, that would give me 2, yes? So I can pull z out once, and I have how many left over? 2. And that's as simplified as that one gets. Now, it kind of gave us a hint with the z squared, because our other radical, the other cubed root, has a z squared. We know we can't reduce that, so it's going to have a z squared. So most likely, since this is all the way reduced, the other one, this radical, should end up as the cubed root of 2z squared. Because if they're going to be the same, this is what they need to be. Okay. So we can bring this down here. Cubed root. Now, we can't take the cubed root of z squared, but we can take the cubed root of 54. Not directly, because if we could just directly take the cubed root of 54, it's going to make an issue, because we need this to be 2z squared on the inside if we're going to be able to add or subtract. They need to be the same. So let's look at the factor tree of 54. What number do we know that goes into 54? 2, well, I'm going to say 2. 2 and 27. The reason I picked 2 is, well, the other one has a 2. I need this one to have a 2. Now, if we look at 27, 27 is 3 times 9, and 9 is 3 times 3. So in 54, Willie, we have 2 times 3 cubed. Which for us means that I can take the cubed root of 3, or cubed root of 27, which is 3, or the cubed root of 3 to the 3rd, yes, which is 3. And what's inside is 2. So any questions on how we got these two here? On how we simplified these two radicals? Okay, now we need to put them back into the equation. Because here, 2z to the 5th became z times the cubed root of 2z squared. So we need 12, because we have 12, what? Z times the cubed root of 2z squared. Minus. Here, we now have a 3 out front. We also have the z from the original problem. Then we have the cubed root of 2z squared. Questions on this here so far? Questions on any of this here so far? Okay. Now that we've done that, both of these here match up, yes? Now, some of you might be wondering, okay, you highlighted a little bit too much, maybe that's just the whiteboard. Well, no, I am meant to include the z's on the outside. Because if we looked at two expressions, say, let me keep writing in the highlighter, is 3x minus 2, can I combine those? Well, no, because they are not like terms. They don't have the same variables, correct? So if one of these two, if this had just been 12z minus 3 with everything else, we couldn't combine them because 12z and 3 are not like terms. We needed the z. The z is included in this expression. So 12z times the cubed root of 2z squared minus 3 times the cubed root of 2z squared. What do we get? What do we get from this here? What would this be? Well, not quite. Because what do they both have in common? They have the z and then the cubed root of 2z squared, yes? So, since this is in common in both, if we use kind of greatest common factor and I factor this out, well, if I factor it out of the first term, I'm left with 12, yes? What's left in the other expression? Negative 3 minus 3, yes? Well, wait a minute, I can do 12 minus 3, yes? 12 minus 3 is 9. Well, we can multiply these together, and the 9 will go out front. 9z times the cubed root of 2z squared. Or up here, 12 minus 3 is 9. So this is the more mathematical way we would technically do this, because we can factor that out, combine these like terms, and get our answer. Questions on this here? Does this kind of make more sense why we can do this? Because even on the first one, I'm going to scroll back up. This one here, 5y plus 6y, well, we easily saw that that's 11y. Yes? 11 square root of y. Well, I could have factored the square root of y out, which would have given us 5 plus 6. Well, 5 plus 6 is 11, so we get 11 square root of y. That's why this works. Okay? What would this be? Yes. Because since both of these expressions have the cubed root of x in it, we can just add the coefficients. So 6 plus 2 gives us 8 cubed roots of x. That's it. Questions on this here? Okay. Let's look at this one here. Now this one here, the radicals are not the same. The radicals are not the same because we've got the fourth root of 3p to the 6, and we have the fourth root of 48p squared. Now looking at both of these here, in the first one, I know we cannot take the fourth root of 3. It's just not going to work. There's not going to be a whole number times itself. 4 times, that gives us 3. Also, 3 is prime. Now, if we look at the other one, p squared, well, I know I can't take the fourth root of p squared and get p to come out. It's not going to come out at all. So, kind of what that's telling me is most likely what? What's going to be left over once we simplify these roots? So we'll have p squared, and we'll also have what? Because can we simplify 3 in the first one? Well, no, we can't simplify it at all, right? So it's going to be left over when we start adding and subtracting, needing to get them to be the same. P squared, I can't simplify it any further than that. So most likely what we're looking for is this root to become the 4th root of 3p squared. Because if they both become that, then we can add or subtract. I mention this because it's almost like a little bit of a hint, something that we can look for that we're going towards. We know where we're headed. Now let's simplify these to get there. Fourth root of 3p to the 6th. Well, we already said we can't take the 4th root of 3. But we can take or simplify the 4th root of p to the 6th. Because we can do our subtraction. 6 minus 4 is 2. Can we do it again? No, we can only pull it out once because we have one group of 4 that will simplify. So we'll have 1 outside. And how many left inside? 2. Well, hey. Those lined up, yes. Let's see if the other one works that way, because that'd be nice. Yes. So, okay, I'm going to write it over here so we can still see everything. 48 is indeed 3 and 16. Well, 16 is 2 and 8. 8 is 2 and 4 is 2 and 2. Well, I've got 4 2's, yes? 2 to the 4th? Well, the 4th root of 2 to the 4th is 2. Which is nice for us because that 2 will come outside the radical. So what's left inside? 3 and p squared. Well, hey, 3p squared and 3p squared. We got the same thing inside the radical, yes? It's kind of what we were looking for. Okay, I've got to erase this here. Now, any questions on how we simplified this here before we start plugging it back in and simplifying? Okay. So we put this back in. P times the 4th root of p3 squared is going to go right in here. So we're going to have 16 times p times the 4th root of 3p squared. Now we're also going to put 2 times the 4th root of 3p squared in for our 48p squared, 4th root of 48p squared, which would give us minus 2p times the 4th root of 3p squared. Any questions on any of this here? Are you ready for the next step? 16p times the 4th root of 3p squared minus 2p times 4th root of 3p squared is what? The 4th root of 3p squared. So really we can do 16 minus 2. Because the coefficients, since everything else, all of this here, and all of this here are the exact same, we can do 16 minus 2, which is 14p times the 4th root of 3p squared. I mean, if we really wanted to get technical on how we say this, I think it would be more 14p times the fourth root of the quantity 3p squared. And then I think in quantity probably would have to added. But we get this here. Because once we get those two radicals simplified down, we can combine the coefficients. Questions on this here? That brings us to the last four. Last four. So we'll see two more of this type that we just looked at, and some that we covered yesterday. Now 13, can we take, so we want to take the cubed root of 27q to the 9th. Well, can I take the cubed root of 27? Well, yes. What is the cubed root of 27? 3. So that's 3. Can I take the cubed root of q to the 9th? Well, yes. Is 9 divisible by 3? Well, yes. So I'm just going to go 9 divided by 3 and get 3. Now, you're probably wondering, why didn't we use the addition or subtraction, or the subtraction method? And it's because it's divisible by 3. We could have done it. We could have said 9 minus 3 is 6. 6 minus 3 is 3. 3 minus 3 is 3. And I did it once, 2, 3 times. The reason I just went on and divided is because I know that 9 is divisible by that index, the index of 3. So if I know it's divisible by it, I won't have any remainders or anything left over. I'll just divide it and get our answer. The reason I would use the addition and subtraction is if I know that there will be a remainder, something left over, something left inside the radical. All right, let's look at 14. Now, we looked at this one yesterday. When we look at this here, when we have variables on top and bottom, inside of a root, so the fifth root of x to the 10th over y to the 5th, what we did is we broke this up. The fifth root of x to the 10th over the fifth root of y to the 5th. Now, we can probably see the denominator, the fifth root of y to the 5th, is going to be y, because the fifth root and fifth power would cancel. Now I'm going to go on and write these in rational exponents. So for x, the exponent is 10, so it goes on top, and our root is 5, so it would go on bottom. Now for this one here, the exponent is 5, so it goes on top. And well, the root is 5, so it goes on bottom. Now for the numerator, 10 divided by 5 is 2. You're good. And 5 divided by 5 on bottom would be 1. Now this here would be our answer. Now we don't have to use absolute values on this for two reasons. One, we took the fifth root. We took an odd root, so we don't need the absolute values. And two, it said assume all values are positive, so we don't have an absolute value. So if this had been an even root, even if we did have something like y by itself on bottom, since it said the exponent, or variables, not exponents, variables are all positive, we don't need the absolute values. Questions on either one of these here? Okay, I'm going to erase that so I have a little bit more room. We have 6xy to the 3/4 over 3x to the 1/2 y to the 1/2. So let's just go from left to right, starting off with 6 over 3. Well, 6 divided by 3 is, it'd be 2. So that takes care of 6 and 3. Now we have x in the numerator and x to the 1/2 in the denominator. Well, since x doesn't have an exponent written, it's automatically 1. And when the bases are the same and we're dividing, we subtract the exponents. So here we'll have x to the 1 minus 1/2. And we can combine those here in a minute. Now this time we do have y in the numerator and the denominator. We didn't have that in some of the ones yesterday. But we'll do the same thing. We have y to the 3/4 minus 1/2. And the order that we subtract these is always numerator, then denominator. The denominator will always be second. Now we need to subtract these exponents. So 1 minus 1/2 would be 1/2. Now we'll have to do 3/4 minus 1/2, which would be 1/4. And again, you could type those into the calculator. The calculator will do 3/4 minus 1/2 easily and tell you it's a fourth. And this here is our answer. Any questions on any of these three so far before we look at the last one? All right. I'm going to write this a little bit over here. We have 9w to the 5th minus, so we have the square root of 9w to the 5th minus w times the square root of w to the 3rd. So we do need to simplify this here. We need to simplify each one of these here. Now this first one here is not too bad, because what is the square root of 9? 3. So w to the 5th. So since we're talking about square roots, our index is 2. Because without a number written in, it's understood to be 2. Now is 5 divisible by 2? Not evenly, right? So let's use the subtraction kind of method. 5 minus 2 is 3. Well, I can do it again. 3 minus 2 is 1. I can't subtract 2 from 1 without going to negatives. So we can pull it out once, twice, because there's 2 w's that we can pull out, or w squared. So we'd have 3w squared, and we only had 1 left inside. Questions on this here? Okay, let's look at the other one. Well, we have minus w. Well, we have w cubed. Well, it's not divisible by 2, so we can't just say 3 divided by 2 and get our number. But we can subtract groups of 2 out, and 3 minus 2 is. So I can bring 1w outside, and we have 1 left inside. So the square roots of w match up, yes? Is there anything else I really need to simplify? Right, this 3w squared, square root of w is fine. Minus, well here, w times w would be w squared. Now 3w squared times the square root of w minus w squared times the square root of w would be 3 minus 1. 3 minus 1 is 2. W squared times the square root of w. And that'd be it. It would be our answer. Any questions on any of this here? Any question on anything we've done so far? No, we're good with this here? Yes? Okay. And that would be if y'all weren't using the books. Okay. Now this is what I'm going to say next, or kind of talk about next, is going a little bit off the note sheet. None of this is included on the note sheets. Now, our exponent properties actually are kind of interesting if we look at them. Because this here, x to the third times x squared, we know that this would be x to the 3 plus 2, yes? And the reason we get at that is because x cubed tells me I have x times x times x, and the next word is x times x. So I've got 1, 2, 3, 4, 5, which would be the same as saying 3 plus 2, yes? Okay, that makes sense, so we can add this way. Now, if we talk about 1 over x to the n is equal to x to the negative n, anytime we move above or below the denominator, we get this negative exponent. Now, if we use these two here, we can actually show the division property. So let's say x to the m over x to the n. Now, our proof right here, 1 over x to the n is equal to x to the negative n. If I move it above or below the denominator, the sign of the exponent changes from positive to negative. So I can move this up, which would be times x to the negative n. That works out, yes? But since the bases are the same and they're being multiplied, well, I can add the exponents, yes? Well, that'd be the same as saying x to the m plus negative n, which is x to the m minus n. Well, that's our property for quotients. If two things are being divided with like bases, we subtract the exponents. So that's kind of why this works out, and it's kind of nice. So I just wanted to show you that there, because we're done.